Alright, so today we are finally going to learn how code is actually run. So obviously you guys probably know how to write a little bit of code, but how it actually runs is a lot more complicated than just writing it in like your compiler and then running it. So let us talk about the basic problem. So first off, like clearly machines and humans are very different, right? So you could probably read C code pretty well, right? On the left you got your C code, and we all understand what that does, right? Like what did it do? It just prints out hello world, hooray. The very simple program, right? But computers don't know how to read this, right? Like there's no way for them to just run this as it is. So essentially all they get is a bunch of zeros and ones. So somehow you need to have a way to get your C code that you could read into something that a computer could read, right? So there's three stages. First, you take the C code and you convert it to the next code. Does anybody know what this second middle part is called? Anybody? It is called assembly code, okay? So essentially this part here is called assembly, right? And it's basically a lot simpler. So you like here where there's a main, there's like a bunch of different types of functions you could run. There's returns, there's brackets, there's all kind of stuff. But in assembly, all you have are these simple commands like push q. You have like some arguments on the right side, and that's it. And then they're converted on the left side to bytes, right? So then eventually this assembly code is converted to machine code, which is literally you see on the right side, like that's the hex representation of the hello world program. All those little like CF, FA, those are all bytes of this program that the machine runs directly. So basically this is how it's broken down, right? So first off, you write a program at a high level programming language like C, right? Then your compiler converts it to an assembly language, and eventually it becomes a machine language that your CPU could run, right? And then your CPU takes these bytes and it uses its CPU to run it using, like you can see, you take in your registers, it goes into an ALU, it does some computation, and eventually it runs your program. And your CPU is made up of a bunch of transistors, right, which are like logic gates and stuff. So that's like this part. So essentially you break down a high level thing down to bytes, and then eventually it's runnable. So today mostly we're going to be talking about assembly languages because these are kind of cool, and essentially the reason why they're cool is because they're super simple and they're really close to machine code. So what do you guys think is useful about having code that's really close to machine code? What benefit do you get from writing code that's very close to machine code? Hint hint, it is why C++ is so good for competitions. Does anybody know?
Because so that makes it faster.
Yeah, exactly, right? Your machine could run your code much faster if it's closer to machine code. Otherwise, it has to spend a ton of time converting it to machine code and running it at the same time, which is why Python's so bad, right? Like Python, it doesn't convert it. You don't compile it ahead of time. It literally runs it and makes the bytecode while it's running it. So that's why it's so slow. So essentially, the reason why we like assembly languages is because they're really close to machine code. And if you're able to write an assembly, you can make really fast programs that are super optimized. And yeah, so basically, assembly is like as close to machine language as humans can code in. So an example is risc-v. So this right here on the right side is a risc-v program, and that is an assembly program. And basically, the reason why they're good is because they could easily be translated to 64-bit or 32-bit instructions. So that is what your 32-bit or like 64-bit CPU, that when it says like, do you want to download a 64-bit or a 32-bit, this is what it means, right? It's basically saying how many bits each instruction is. Okay, so the reason why we're going to be talking about RISC is because it only has 47 instructions. That is kind of crazy, but it literally has 47 instructions that are able to run all this kind of stuff. So essentially RISC stands for reduced instruction set computing, right? So that's why it has so few. And essentially the basic format is function, argument, right? So basically you have add t0, x0, x0. It basically adds x0 and x0 and puts it in t0, right? So this is the same thing as saying t0 is equal to x0 plus x0. Okay. So essentially these t0 and x0s are called registers, right? So essentially your normal C code has something called variables, right? And those are stored in random access memory, right? So that's your RAM, right? But your CPU actually has like a tiny bit of memory by itself. So essentially have these registers that store exactly like one integer, and those basically are used for quick computations. And RISC has 32 of these registers where x0 is always 0, t are like temporary variables, and a is argument, right? So does anybody have an idea what this code right here, these two lines might do? So I told you that the So what's t0 going to be at the end of this code? Could anybody tell me? Any ideas? So add basically takes the second two things and adds them and stores them in the first thing. So what is t0 going to be at the end?
It's 5.
Yeah, exactly, right? So you say 0 plus 0 is equal to t0, and then here you do t0 is equal to t0 plus 5, so t0 is going to be 5. Okay. And then in the top right, you can see like that's like C code at the top, assembly code in the bottom. You're basically loading the first thing into t0, you're loading the second thing into t1. You are storing the thing in t1 into the first part of the array, and then you're storing the thing in t0 into the second spot of the array. Okay. So we are going to code up Fibonacci together, so it's going to be fun, and we're only going to use 5 commands, okay? It's going to be epic. So the first command we need is add a, b, c. So a is equal to b plus c. Then we have add I, where a is equal to b plus c, except c is an integer, right? Doesn't have to be a register. Branch of equal basically means it jumps if the two are equal, and then move ab basically moves b into a, and then jump a moves jumps from one function to another. So why don't we code this up? So this right here is the Fibonacci code in C++. Let me see if I can zoom in properly. All right. Okay, and then we'll put the other thing over there. Okay, so first off, basically this part just prints out whatever is in t0, right? So right now it's going to print out 0, right? If we go to simulator, we assemble, simulate, run, you can see at the bottom it prints out 1, right? Okay, so, or wait, yeah, because it adds 1, so I'll change this to 0. And then if we made like t05, right? If we make this, hold up, make this add I t0, t05, then what would you expect it to print? That's right, you would expect it to print 5. Okay. Very epic stuff. Hold up, did someone send something to the chat? Okay. Never mind. Okay, so alright, so what's the first step? Okay, let's just say that f0 is t0 and f1 is t1. So what do we want to do to set f0 to 0? Well, we already have t0 is x0 plus x0, so we got that. What about this one? How do we do this? Anybody have an idea? Anybody? Go on. How do you set something to 1? No ideas. Cliff? Okay, I will give you guys a hint. Okay, so we're gonna say t1, right? Right, and then we want to do 0. Okay, so if we want to do 0 plus 1, how could we do it? Any ideas? Nobody? Okay, well, we set this to x0, we make this a 1, right? So now we're adding 0 and 1, and we're putting it in t1. Okay, now we also want to do I. What should we do I? Let's just say it's t2, right? So we'll do, so what do we want to set I to originally? So what do we do? What's our next command? If we make I as t2. Anybody?
You add t1 and t2.
Say what again?
You add t1 and t2.
Add t1 and t2?
Oh wait, no, you make t2 as like t1 plus t0.
Well, you want I to be started at 0, right? So how do you make I?
Then you make it x0.
X0 and?
x0.
Yeah, exactly. Okay, so now t2 should be x0. Okay, now I'm just gonna do n for you guys, so I'll just set like add I. Let's say what should we make n? Let's just say t3. Okay, so n is gonna be t3. So if we want to set it to something like, we could just say, let's say we want the 9th Fibonacci number or something. Okay, so now n is just 9. All right. So now we need to do our for loop. Okay, so let's just say that we have basically the structure of this is we want to go down to the bottom of our for loop and then jump back to the top, and then at the top we want to check if I is too big or not, right? And which of these commands do you think will be useful for jumping? Which of these commands do you think will be useful for jumping back to the top of our for loop?
J.
Yeah, so let's just say for loop right here, we'll call it like for or something. Okay. And then we'll have, at the very end of it, we should have j to where? We want to jump back to the top, right? So what function are we going to call again? I mean, okay, I'll just say it. So you jump to 4, right? Okay. And then now, at the very top, and then what do we want to do every time we finish a for loop, right? Like, in a normal C++ program, what happens to I every time you finish a for loop?
You increase it.
Okay, so what are we going to do? How do we increase I by 1?
You just add it.
Yeah, so what'll be the command? So add I.
And then like x comma 1 or something.
Well, what register were we storing I in?
Was it T0?
I mean, yeah, we could,
no,
but I originally said T2, so let's stick with T2, right? Okay, and then we do, well, how do you add 1 to it? We want to set T2 is equal to T2 plus 1.
Do T2 comma 1.
Yeah, okay. Very nice. So now we want to do the logic. So essentially, 1 is going to be printed out, or sorry, 1 is going to be, wait. So basically at the top, I is going to keep getting bigger, right? And eventually we want to stop it. So when do we want to stop? Which of these like has a conditional?
Wait, branch BEQ.
Okay, so we're going to say BEQ, and we want to check if A is equal to B. So when do we want to stop? So BEQ is going to be called when we wanted to stop, and when do we want it to stop? Which two things have to be equal for it to stop, right?
Well, T2 and T3 are equal.
Yeah, exactly, right? If I is equal to n, then we want to stop it, right? So we're going to say if T2 and is equal to, sorry, we're going to do, yeah, T2 is equal to T3, then we will break to, let's just call the end finish, right? Finish. Okay, and we're going to jump to finish. All right. So why don't we print stuff out in this for loop just to show you guys that it's working. So we do add, hold up, add I, A0, X0, 1, and we'll do add A1, X0, X0, let's say. Okay. So if we simulate this, hold up. Oh, whoops, I don't want to terminate it during the thing. Okay, that was not a very big brain move. Okay, so put that here. Okay. So you can see, right, we got 9 zeros, hooray, our for loop is working. Okay, so now we got to do what's inside the for loop, right? So let's go here, and we got this. Where is this? Okay, so what do we do in the for loop? Any ideas? What is the first thing we got to do in our for loop?
Just make another variable.
Yeah, so hopefully, I'm pretty sure they're the T4, so we'll do, what do we do? Anybody? If temp is equal to T4, then which command do we use to set it equal to F0 plus F1?
Like add I, T0, A0, A1.
Well, if you're doing two registers, you should just use add, but yeah. T0, or T4, T0, T1. Okay. So now we got temp, alright. Then what? Want to set F0 to F1. How do we do that?
So like add T0 equals T0, T0. Sorry, T0, X0, T1 or something.
Oh, that works. Yeah, that's one way to do it. And yeah, you basically just figured out like the move is the same thing as like just adding. So yeah, we'll do that. So T1, X0. And then what do we want to set T1 to? Anybody? Come on, fine.
T4.
Yeah.
X0.
Okay. So you got that, and then at the very end, which register do we want to print? Do we want to print which one? Okay,
T0.
well, yeah, T0. So then if we just run this, does anybody know off the top of their head what the 34th Fibonacci number is? No, sorry, ninth Fibonacci. Oh, I gave it away. Okay, you know what? What's the 10th Fibonacci number? If 34 is the
55.
what? 55? Is it? I don't know. Let's see if you're right. Hey, you are right. Good job. Very nice. All right. So we made our Fibonacci thing. Okay. So let's get back to this. Basically, whoops. Basically, we have a challenge in the CTF website, which is basically like make your own exponential function, which is similar to this, except it's a little bit more clever. So if you guys want to try that out, try that out. But how do you think these risc-v instructions are converted to bits? So let's just do a little bit of arithmetic. How many instructions did I say we had? Anybody remember? No, we have a lot more. Well, that's how many we used in our Fibonacci, but how many total do you think risc has? Like guess, if you don't remember.
Like 32 or something.
It's a little bit more, but it's 47. So it's pretty close. It's like really small. So how many bits do we need? So if each bit is a 0 or a 1, right? How many bits do we need to encode 47 instructions? Okay, how many instructions can 1 bit encode?
2.
2, right? Okay, then how many can 2 bits encode?
2 to the power of 2.
Exactly, right? So it's 2 to the power of n. So if you want to get 47 instructions, how many bits do you need?
6.
Exactly, you need 6 bits at least to encode your 47 instructions. How many registers do we have? Anybody remember? I think Nikhil already said this, but do you remember anybody?
32.
Yes, we have 32 registers. I think that's where you got 32 from. So we have 32 registers. How many bits do we need to do 32? Come on.
5 bits.
Yes, you only need 5. Okay. So essentially, for an add-I, right, for example, you would have a 6-bit thing to tell you what instruction to do. Then you'd have like a 5-bit for the first register, 5-bit for the next register, 5-bit for the last register, and hooray, you got an instruction. So essentially, this is basically literally how it works, right? So this is a lot more complicated than that, right? But you essentially have 5 bits for your like destination register. You have 5 bits for your other register. You have like 5 bits like all around here. So that's essentially how it works. And then you got your opcode, which tells you which instruction. I'm not going to go into detail because it's like kind of boring. And if you really wanted to, you could search it up. But that's the essential way it works. Okay. Okay, so now that we've talked about assembly, right? We now need to talk about who actually runs the code. So there's a difference between compilers and interpreters, right? So interpreters are what actually read the code and execute it. So like, for example, as I told you before, Python is like, what do you guys think Python is? What type of language? Is it a compiled language or an interpreted language? Any ideas? Well, the reason why it's interpreted is because it directly runs the Python code. It doesn't convert it to machine code and then run it. It runs the Python code directly. So that's why it's an interpreted language. The interpreter directly reads the Python code. So essentially, you can see the trade-off here, right? So machine code is really hard to program in. Good luck like actually coding in bytes and bits and actually writing out zeros and ones to tell your computer what to do. But it's a lot easier for the machine to interpret, and it's way faster, right? But we kind of want something that's easy to write in, so Python's on the left side of this whole thing. Okay, so essentially translation is another option, right? If we have a really easy to write language, we might as well convert it to something that's easier for the machine to run and then run it, right? So that's basically what C does. Okay, so this is basically the reason why Python is so hecking slow, and it literally, every time it runs a line of the code, it literally converts it to bytecode and then runs it, so it's really slow. But it basically is less efficient, but it's also good, like a lot easier for new people to code. So this is the summary of how it works, right? You basically have a compiler that like converts it to assembly. Your assembler like puts together, like it converts the assembly to machine code, right? Then your linker, like, okay, so if you import functions, how do you think they actually get into that like code that runs? That's literally what the linker does, right? So if you call like the standard library, it pulls the function from the other file and then it puts it in your executable file, and then that's how it runs that, right? It literally brings in functions from other things and puts it in your file. That's why you're like, you know how the hello world thing was so long? That's because it actually brings in the entire print function from another library, and that's how you run that. And then loader basically just puts it in your CPU, runs that. So very cool stuff. So I mean, yeah, so we could just like, let me give you the flag first, I guess, and then I will show you just me actually putting in the C++ code. Hold up. Okay, there's the meeting flag, and then let me bring up my terminal. Okay, where is the C file? Okay, vim test.c. Okay, so you see this is how our C code looks, right? Then if we want to convert it to a, if we want to compile it, we do gcc-o test.c, right? Okay, then if we cat test, right? It's all this gibberish, right? So this is literally machine code. There's a bunch of bytes that we can't read. There's some stuff that we could read, but literally it's all bytes, right? And if we wanted to see the assembly code that created it, we could do objdump-d test pipe less, and then hooray, here's all your assembly code. And this is the bytes that it's converted to. So that is cool. And basically, if we run the executable, hooray, you get hello world. Very cool stuff. All right, does anybody have any questions? Because other than that, I am done for today. Anything? No, okay. Well, on the CTF website, I put like a link to one of the UC Berkeley labs for CS61C. It's pretty cool stuff, so if you want to do that, they probably will explain it a lot better than I did. And it's also a little bit more advanced, so if you're interested in that. And then another thing you can do is the exponential challenge if you want to do that. Okay, well, that's it for me, so if you guys are done, feel free to drop out.